All right, good evening. My name is Hunter, and this is content review for general chemistry students, Portland State University. This is the week 6 topic, so we're going over thermodynamics and a couple specific topics, including entropy, enthalpy, and Gibbs free energy. First question we're looking at here, second and third law of thermodynamics, calculate delta S naught. Delta S naught means the change, delta, the triangle, is always a change in entropy, which is a measure of chaos or disorder um, in the universe, not this little circle in the top right, just means that it's at standard conditions, so standard temperature pressure. So calculating the change in entropy for the following changes, and we're given this balanced chemical equation. Because we're working at standard conditions, you can use tabulated values for this. So I've gone ahead and looked those up for you. And I'm going to add my coefficients to these just as a good practice. So this is the standard entropy for the formation of each compound. And this is all in units of joules per mole dot Kelvin. All right. So approaching this problem, the total change, this is going to look a lot like equilibrium problems that we were looking at in the previous weeks. It's just products, relating products with reactants. So in this case, the total change of the reaction at standard conditions is the sum of the change of standard entropies of products minus the sum of the change in entropies of reactants. So for this particular reaction, we have products minus reactants. 365.8 minus 258.6. Plug that into your calculator. You should get 107.2, and this is in joules over mole dot Kelvin. This makes sense because if you look, so we have a positive value here, which means that entropy is increasing, disorder is increasing. And in our balanced chemical equation, we saw that we were going from a liquid to a gas, and that change in general should result in an increase in disorganization. So that checks out. Same story for the next one, but now we have some stoichiometric coefficients to worry about. So we have our standard entropy of dihydrogen gas. We've got our coefficient of 2 times 130.7, that's joules per mole dot Kelvin. And for diatomic oxygen, we have 1 mole of it, and it's 205.2. And then we have our liquid water as our product, and that is, we have 2 moles, and that is 70. So same deal. The total change in entropy for the reaction is our products minus the sum of reactants, products minus, and I'm going to use brackets here to kind of help me keep track. We have 2 times 130.7 plus 205.2. If you're not already in the habit, get in the habit of using these brackets. You can kind of keep track of your orders of operations here. Simplified, 2 times 70 is 140 minus 2 gives us 466.6. 140 minus 466, we're going to get a negative number, or we should. Is that right? .6 joules moles dot Kelvin. And that makes sense. We're going from gas to a liquid. So a negative entropy means we're decreasing disorder or increasing the order of the system. And so a negative entropy value makes sense here. Question 23, determine the entropy change for the combustion of gaseous propane, or C3H8, under the standard conditions to give gaseous carbon dioxide and water. So we're given a couple of hints here. Combustion reaction. This is a strong oxidizing reaction. And they've given us a chemical formula, which is helpful, and standard conditions. So we know we're dealing with that delta S naught value. And so we can use tabulated values. Let's start by getting our balanced chemical equation in order, because we need to know our our stoichiometric coefficients here because we're not given them. So a combustion reaction, you're always adding oxygen, and your byproducts are always going to be CO2 and H2O, both gaseous. So all gases in this system, so we can't just look at the change in states. There are no phase changes here, but we have some other hints that we can kind of work with. So balancing out this chemical equation, we'll start with the carbons. We've got 3 carbons on the left, only 1 on the right. Let's give that 3. Check our oxygens. We're going to have to balance these out, and we've got an odd number on the right. So let's go ahead and get 5 of those, because we've got 6 here, and now we can do 4 here, and that gives us 10. And now this should be balanced. So again, we're going to look at tabulated values for the standard entropies of these chemical species. For our gaseous propane, we're looking at 70.3, 270.3. We have 5 moles of our oxygen at 205.2. 3 moles of our CO2 at 213.8. And 4 moles at 188.8. Okay, so we're halfway there now. We have all of the values that we need to be able to solve this problem. It's just like the one we just did. Change in entropy for the entire reaction. We have products minus reactants. We have products. CO2 was there, plus 4 times 188.8 minus our reactants. 270.3 plus 5 times the quantity, 205.2. Plug that into your calculator. We're going to get, I like to break these up. So doing our reactants first, we get our total there minus our total for reactants. I may have said that backwards. Products minus reactants, always. And our total is going to be 100.3 joules per mole dot Kelvin. So this is a positive value, so entropy is increasing. Does this make sense? This is a combustion reaction. We're lighting something on fire or it's exploding, so we can kind of intuit that this is going to be a reaction that should increase in entropy. So it makes sense. Question 27. By calculating the change in entropy of the universe at each temperature, determine if the melting of 1 mole of sodium chloride solid is spontaneous at 500 degrees Celsius and 700 degrees Celsius. So we're given a couple different questions that we need to answer as part of this problem. Remember that our units for entropy are in this joules per mole dot Kelvin. Our temperatures are in Celsius, and we have a delta H value, enthalpy, in kilojoules per mole. So just be very, very careful with your unit conversions. And if you need to, make a table first that converts all of these values for you, or convert these values first, so that as you plug them in, um, you don't make any conversion errors. The other thing that we need to look at is the relevant equation. So we're not working at standard temp and pressure anymore. We're given non-standard temperatures. And so the equation that we're going to use here is the change in entropy of the universe equals the change in entropy of the system of interest plus Q, which is a measure of heat, and this is going to relate to our enthalpy, divided by the temperature in Kelvin. And generally, when we're looking at Q and the heat, we're looking at the change in surroundings. We just need to be careful with our signs here. So how do we want to do this? So Q relates to heat, temperature we're given here, and we need to figure out the change in our system. So let's give ourselves a balanced chemical equation like we did before, from solid to liquid. There's no stoichiometry to worry about, which is nice. But for our solid sodium chloride, we have a standard value at 72.11. And for liquid, we've got 95.06 joules over mole dot Kelvin. So our standard change is just 95.06 minus 72.11 gives us 22.95. Before we go any further, let's go ahead and get our other units in order. So 500 Celsius plus our conversion factor, 273 Kelvin, gives us 773 Kelvin. I'm going to highlight that so we know that's the one we need. And we have 700 degrees Celsius plus 273 gives us 973 Kelvin. Okay. So we'll do our 500 degrees Celsius first, and we're just going to plug in these other values that we have. So a little crowded here, but the change in entropy of the universe is our delta S naught for the system, so 22.95 plus the change in heat. So our Q value was 27.95 divided by our temperature, 773. No, it isn't. This is times 10 to the third because it's in kilojoules per mole. So be careful there. And this is going to be a negative value. I'm going to go ahead and go back over this in red just to be careful. This is a negative value because it's the change in enthalpy of the surrounding. And so plugging these values into the calculator, the change in entropy in the system should be negative 13.2 joules per mole dot Kelvin. And because this is a negative change in entropy, disorder is decreasing. This is very likely not a spontaneous reaction. So we can use this same equation and just substitute in our temperature value at 700 degrees Celsius. So 22.95 plus negative 27.95 times 10 to the third, and divide by 973 this time. And we should get a value of negative 5.8 joules over moles dot Kelvin. And this is still not spontaneous because there's still a decrease. So what assumptions are made about the thermodynamic information, entropy and enthalpy values used to solve this problem? Um, First is that for entropy, looking at those delta S naught values, we were working at standard temp, which is 298.15 Kelvin, if you want to be more precise. And for the enthalpy value, we were working in non-standard temperatures. And making some assumptions that using the standard enthalpy values, oh, it's hiding behind my face now, using those standard, excuse me, entropy values, um, the difference would not be significant enough to impact this calculation. Um, so the enthalpy at non-standard conditions is what was useful to us here. Okay, so free energy, what is the difference between delta G and delta G naught for a chemical change? G simply stands for Gibbs free energy, so named for the scientist who described this relationship. And this is typically reported in kilojoules per mole. So delta G is the Gibbs free energy at non-standard conditions. So this can be used for pretty much any reaction. And the standard Gibbs free energy is at standard conditions. You may see that as STP, and that is 1 atmosphere and 298.15 Kelvin. So again, we're going to be looking at tabulated values in the textbook. I've looked those up for you so that you don't need to be going back and forth, but it's just a good habit to be in when you see those standard values for that delta G naught or delta S naught, you know that you need to be referring to the textbook or to something that's provided to you in the text of the problem. So using the standard free energy data in Appendix G, determine the free energy change of each of the following reactions, which are under standard state conditions and 25 degrees Celsius. Identify each as either spontaneous or non-spontaneous at these conditions. So our standard Gibbs free energy of F of formation for copper is 0, for sulfur is 238.25, and for copper sulfide is negative 86.2. Now our standard Gibbs free energy of the reaction, very similar to what we were looking at with entropy. It's simply products, the sum of all products minus the sum of all reactants, PDT minus the sum of all reactants. So we can simply plug this in. Products, negative 86.2 minus, we've got, we don't have to worry about copper, it's 0, so just 238.25 equals negative 324.5. Now, here are some rules that you're just going to have to remember, or you can kind of understand based on the relationships. If Gibbs free energy is less than, equal to, or greater than 0, if Gibbs free energy is less than 0, this is a spontaneous reaction. At 0, it's in equilibrium. And if the Gibbs free energy is greater than 0, this is a non-spontaneous reaction. So this is a negative Gibbs free energy. It's less than 0, so this would be spontaneous, right? And we couldn't get there just by looking at our state changes, right? Um, although maybe we could, because we're going from a solid and a gas to just a solid, incorporating that gas. So you could intuit just from the phases of the species that there is a decrease in disorder as well as um, this negative Gibbs free energy value. All right, let's look at iron oxide. So Gibbs free energy. Actually, you know what? I'm going to go ahead and skip this one just because it's going to be more of the same. But I'll go ahead and write these values here for you. Don't forget your stoichiometry. And give you a shot at doing this on your own. And I believe, well, maybe not. Um, be careful with your stoichiometry, products minus reactants. All right, 39. Calculate the change in standard Gibbs free energy for each of the following reactions from the equilibrium constant at the temperature given. So we're not working at standard conditions anymore, but we are calculating a standard change in Gibbs free energy. And the equation that you need to have memorized to be able to solve this is that the Gibbs free energy at non-standard conditions is negative RT ln K. And K is any constant. In this case, it's going to be our equilibrium constant. R is another value that you're just going to have to memorize. In this case, it's 8.314, and that's joules over mole dot Kelvin. You're also going to see 0.0821. Yeah, and that's when you're working with liters, atmosphere, mole dot Kelvin. We don't need that one today, but that is just review for you. And then for temperature, we're given a temperature of 980 degrees Celsius plus 273 gives us our Kelvin, which is 1,253. And then we're given our K value as well. So this is a real straightforward plug and chug. We're given all of the values that we need. Delta G equals negative 8.314 times our temperature times ln of 1.67. And we should get, plugging this into our calculator, negative 5,342.3 joules per mole, or some units cancel out here. And we're going to simplify this to negative 5.34 kilojoules per mole. Okay. Yeah, this one we truly, again, we can't really look at our phase changes. We can't even look at whether there's a addition or subtraction of the number of species from reactant to product side. There's just an exchange happening. And so we really do have to look at the tabulated values in this case. And to find out that, yes, this is a Gibbs free energy of less than 0. So this is also a spontaneous equation or spontaneous reaction. All right. Hydrogen fluoride, aqueous with liquid water to aqueous hydronium and fluoride ions. We're at standard temp, so that's nice. and we have our equilibrium constant. All right, so same deal. Delta G, negative RT ln K. R equals 8.314, and that's joules over mole dot Kelvin. Temperature is 7.2 times 10 to the negative 4 plus, sorry, that's our K value, 25, 25 degrees Celsius plus 273 is 298, and then we're given our Kp. So delta G equals negative 8.314 times 298 ln 7.2 times 10 to the negative 4 equals 17,928 joules per mole dot Kelvin. Divide by 1,000. 17.9 kilojoules per mole. Excuse me, that does not need a dot Kelvin there. Kilojoules per mole. Okay. Calculate the equilibrium constant at 25 degrees Celsius for each of the following reactions from the value of the standard Gibbs free energy given. All right. So let's solve A first. So since we're starting with, rather because we're trying to come up with the equilibrium constant, we're going to use just a different form of the equation that we were working with before. E to the power of something is how you get rid of the ln in the equation, but it's a related equation. So E to the power of negative Gibbs free energy over RT gives you your equilibrium constant. So we've got, and we can just plug in our values here, being careful again with our units. So K equals E2. We're looking at this one here. So we've got negative times a negative 10.88. Nope, excuse me. Yes. This is in kilojoules per mole. We need it in joules. So just times 10 to the third divided by, we're at 25 degrees Celsius. So 293. And our R constant, 8.314. Be careful putting this in the calculator, but you can just hit second ln, and that'll give you E raised to the power of automatically. And you can just type in, we've got a negative and a negative, so it's just a positive 10.88 times 10 to the 3 divided by 293 divided by 8.314 gives us, oh, I got a little bit different value. Let me make sure I did this right. Yeah, where'd I go wrong here? Hang on. Ooh, I bet I know where I went wrong. E to the power of negative. Ah, you know what? I should do this separately first. 293 divided by 8.314. So K equals E to the negative 4.466 I'm still getting something weird here from what I expected. Should be. Good catch. So my temperature value was incorrect. 298. Let's try that. We've got 10.88 times 10 to the 3 divided by 298 divided by 8.314. That looks more right. So we've got e to the power of 4.39 something. I'm still getting something mismatched here. I really don't want to lead you guys astray, so I want to make sure I'm 100% here. $298, 8.314. There we go. Okay. I was just hitting a wrong key. So we should get a value, 80.75, 5775. So this is a K value great, whoa, come on. K is greater than 1, which means at equilibrium, um, we'll have more products than reactants. This should be spontaneous, which tracks with our negative Gibbs free energy value. All right, let's see if we can amend our mistakes for the next one. And we've got raised to the negative 3.4 times 10 to the 3, 298 as our standard temperature, and 8.314 as our R value. I'm going to check this again. 3.4 times 10 to the 3 divided by 298 divided by 8.314 to the negative 1.372, etc. gives us 0.25. So we have a K value less than 1, so it will not be spontaneous, which makes sense given the positive Gibbs free energy value that we have. So that tracks. All right, given the standard Gibbs free energy for lead, 2 plus aqueous, and chloride aqueous is negative 24.3 kilojoules per mole, be mindful of units, and negative 131.2 kilojoules per mole, respectively. Determine the solubility product for lead chloride solid. All right, so again, we're going to be working with this same equation. R equals 8.314. We're dealing with a standard Gibbs free energy, so we can infer that our temperature is at 298 Kelvin. Let's write our balanced equation. We have we're trying to do the formation. Let me think here. Yeah, I'm going to write it this way. So we'll start with products here because the formation of, we're given formation constants for lead, aqueous, and chloride, aqueous. Balancing that really quick, we have a 2 there. Um, our formation, since it's standard, we're just going to have to look this up. So this is a tabulated value at negative 314.1 kilojoules per mole, negative 24.3, and negative 131.2. Standard Gibbs free energy of the reaction. We're just going to do products minus reactants. Gives us 24.3 plus 2 times 31.2 minus negative 314.1. All our units are the same, so we don't need to do any conversions here yet. It's plus a positive, and that's going to give us delta. The change in Gibbs free energy for this reaction in standard conditions is positive 27.4 kilojoules per mole. So now we need to go from this change in Gibbs free energy to a solubility product, or to a solubility product. So our KSP equals, we're going to use that same equation, negative 27.4. We need to be in joules per mole now, so times 10 to the third. I can feel that my tablet's overheating. So there's a really great question in the chat, and that is how precise would we be expected to be if we use 298 for temperature? I guess this is in the previous problem. Yeah, this was in 42A. So let's go back. This is worthwhile to talk about. If you use 298, you get 80.75 as your final value. But if you use 298.15, it's 80.57. So technically, you are correct that it would be more precise to use the total value. And if your professor is generous, they will allow you to make certain approximations. If they want you to be more precise, be more precise. I use the 293 value because it's a reasonable approximation for the purposes of getting the answer right on a multiple choice test. It's barely less than the actual value, and so if your value ends up a little bit lower, then you can kind of infer which of the multiple options is probably correct. And that's just a strategy for test taking specifically and getting close enough to the right answer. So that's kind of up to you. As long as you know what you're approximating and you know what the actual value is, go ahead and use the more precise one because you will get a more precise answer. And then carry your significant figures all the way through your calculations until you get to your answer, is my advice on that. All right, let's get our solubility constant. We have R is 8.314. And our temperature, are we working at standard temperature? Yes, we are. So it's 298. gives us E2. I'm going to check this again because 27.4 times 10 to the third divided by 8.314 divided by 298. Hmm. All right, I'm getting something weird again. 27.4 times 10 to the third divided by 8.314 divided by 298. That's frustrating. It's not even close. Okay. Where did we go wrong? 27.4 times 10 to the 3 divided by 8.314, 298. I have to be hitting something wrong on my calculator. This is ridiculous. There we go. Okay. That's what we expected. Okay. We should get 1.57, yeah, times 10 to the negative fifth. It's a very, very, very small solubility product. It's like a million degrees in this room all of a sudden. All right, last problem for the day. In glycolysis, 1.58. Yeah, I think that's close enough. The hemming and hawing I was doing is whether my additional figures warranted rounding, just because it's kind of close. But I think you would get that correct on an exam. All right. In glycolysis, the reaction of glucose to form glucose 6-phosphate requires ATP to be present as described by the following equation. And we're given the total equation here with a negative Gibbs free energy, and so it is spontaneous as written. In this process, ATP becomes ADP through dephosphorylation, summarized by the following equation. So we have a Gibbs free energy for the dephosphorylation of ATP to become ADP. Determine the standard free energy change for the following reaction and explain why ATP is necessary to drive this process. I'm going to be a little redundant here, and I'm going to rewrite the equation we were given because this is just a good accounting step. G6P plus ADP. Gibbs free energy for that equals negative 17 kilojoules. We don't need to worry about units right now because they're all going to be the same. We need to get to an equation that is just glucose and G6P. And to get there, we are going to subtract the intermediate reaction. So to cancel out the ATP, we have to get it on the product side, which puts our ADP on the reactant side. And our delta Gibbs free energy for that was negative 30 kilojoules, but we're flipping it, so it's positive 30 kilojoules. ADP cancels out, ATP cancels out. Now we simply sum these because all we're left with is our glucose and G6P. Negative 17 plus 30 gives us a standard Gibbs free energy of 13 kilojoules. This being a positive number means that it's non-spontaneous. And so in order to get from glucose to G6P, it has to be coupled with the energetically favorable dephosphorylation of ATP to ADP. Requires energy from ATP to proceed. So this is a topic that you'll get into in a lot more detail if you go on to biochemistry, and you should already be seeing some simple versions of this in your biology classes. This coupling of a energetically unfavorable reaction, glucose to G6P, with an energetically favorable reaction, ATP to ADP, makes the overall reaction favorable and spontaneous so that it can proceed, which is just a cool thing about how life works. That's everything that I have for you today. Get some sunshine in your eyeballs, enjoy the weekend, and I will see you all next week.